Thank you, Alicia. It really is a pleasure for me to introduce someone who is not only a great physicist and a valued colleague, but also a dear friend. Steve did his undergraduate works at Bates College in Lewiston, Maine, and some of you may know this renowned liberal arts college as the home of Nathan Lundblad, who is a prominent visitor to JQI, as well as being an alum of the Laser Cooling Group. Steve got his PhD from Princeton in 1977, and after postdoctoral work at Indiana and at Chalmers, he joined what was then called the National Bureau of Standards in 1979, and that's where I met him around 40 years ago. In 1987, close to the time that NBS changed its name to NIST, Steve went to Indiana University and then in 2001 to Yale. And there, in addition to being a professor of physics, he, shall we say, served time as the deputy provost for science and technology and for research. Throughout his career, Steve has made stellar contributions and breakthroughs in a range of quantum topics, of which we're going to hear a little bit today. He is among that small but extremely valuable group of people, superb theorists who understand experiments. Recently, the Yale News reported that he's been named the director of the Co-Design Center for Quantum Advantage, a $115 million operation where he will oversee and coordinate the efforts of 88 senior research scientists across 24 institutions. All I can say is better than you than me. Finally, I want to say that Steve is a great friend of the JQI, and we have been the beneficiaries of his sound advice and his wisdom and understanding many times. And in fact, Steve helped establish NIST University of Maryland Ties in 1987 when he co-edited a Springer book on the quantum Hall effect with Richard Prange. If we were meeting in person, it would be my pleasure to present Steve with a token of my appreciation, the green bound government issue notebook that Steve developed an affection for when he was at NBS. And I'm sure that most of you have seen me use this book at the JQI seminars and other seminars around. And Steve, I promise you that when we can finally meet in person, I will give you a few of these. Steve, the floor is yours.
Thank you very much. I'm probably not alone in noticing that my friend Bill over the last few months has begun to resemble more and more Gandalf from the Lord of the Rings. And so I want to hold up my Palantir shirt, and I hope that you will all help us save the Shire. Okay, so I find it quite difficult to see the raised hands so while I'm talking, so I'm happy to just have a verbal interruption. And don't worry about, let's see, I have two choices of windows here. To share, let's see if this one works. Okay, that looks like it's working. And let me get out my, oh no. Get my laser pointer working here, just a second.
I think just pointing with the mouse is pretty fine. So if that's easier.
Yeah. Okay.
Laser pointer is excellent. Yeah.
Yeah. Good. So, so I want to talk to you about circuit quantum electrodynamics, the QED of superconducting microwave circuits, and talk about how to use them for quantum simulations using a sort of hybrid architecture that involves discrete quantum variables, qubits, and continuous quantum variables, harmonic oscillators, resonate. I'm going to use oscillator, resonator, cavity, all interchangeably. And the work experimental work I'll be telling you about comes from the labs of my colleagues Michel Deveray and Rob Sholkoff, and a great number of people have also contributed to the theory. So good. So again, please feel free to interrupt with questions. So I'll just start with the sort of obvious, that if I have a discrete variable system, in this case, transmon qubits, there are approximately two-level systems. And the Hilbert space, if you have, let's say, three of them, is a direct product of three effective spin-a-half systems. So there's a total of 8 states in the computational basis, and you can label them by the Z component of the pseudo spin that describes these two-level systems. And the states run from, just like the binary numbers, from 0 to the binary number for 7. If you have a continuous variable system, it might be a two-dimensional coplanar waveguide resonator made out of a superconducting bar with ground planes on each side. Or it might be a three-dimensional empty box made of superconducting aluminum, machined out of superconducting aluminum. And there are many microwave modes inside such a box, but because the box is only a half or one wavelength on a side, the mode's spacing is quite large, and we can focus often on a single particular mode, which is, and each of those modes is a harmonic oscillator with the excitation number of the oscillator representing the number of photons in that mode inside the cavity. And you could have the same, represent the same quantum information, the same quantum amplitudes as for 3 qubits by using Fock states 0 through 7. So photon number states. So there's an isomorphism between qubit states and oscillator states. The oscillator photon number is unbounded, but if you want to have an isomorphism with a set of m plus 1 qubits, then the total photon number you need is exponential in that, 2 to the m plus 1 minus 1. So you have to be a little careful if you tried to represent too many qubits. If you wanted to try to say, oh, a single empty box, a resonator, is a very simple object, and I can use it to represent multiple qubits. That's actually true, but you don't want to try to represent too many qubits, because the highest excited state of the oscillator you have to use will have exponentially many photons in it, and even a slight damping will eventually become overwhelmingly important. Conversely, you might think that if I wanted to represent a bosonic mode, an oscillator, using discrete qubits, that would be very efficient because I would only need log of the n max qubits. And that's true, but it turns out to be quite difficult, as I will explain. So I'm going to start with some introduction to the Hamiltonian that we have in circuit QED for a single qubit coupled to a single mode oscillator, and show you that we can gain universal control of the joint system, and we can make fancy measurements of the hybrid qubit oscillator system to do rather efficient complete state tomography. And then I'll describe the general idea of simulation of physical models containing bosons, and then give you a specific example involving the molecular vibrational spectra of triatomic molecules. Another area in which hybrid qubit oscillator systems are important is in quantum error correction, but I've decided that I I didn't have time to cover that today. I also apologize that there's some trees being cut down and chipped up outside my window, so I hope the noise is not too disturbing. Okay, so let's talk about control and measurement of these systems. So as a simple example, we have a three-dimensional cavity with a particular electromagnetic mode in it containing various numbers of photons. And we have a transmon qubit, a superconducting antenna with whose two halves are connected by a Boson junction to make it an anharmonic oscillator and act like a two-level system. And if you detune the so the oscillator is the single mode of this cavity that we're focusing on is a harmonic oscillator with some frequency omega cavity. And to a certain approximation, the transmon is a two-level system with a Hamiltonian given by the qubit frequency times the Z Pauli matrix, describing the two states ground and excited. And then because of the large dipole moment of the atom talking to the electric field of the photons, there's some dipole coupling, but it's virtual because the frequency of the cavity and the frequency of the qubit have chosen to be quite different. But in second order perturbation theory, you get an effective so-called dispersive coupling of this form. And this is going to be our workhorse on which we're going to base everything. And the fact that this is a dispersive coupling is extremely strong because our atom is a millimeter in size, is going to be the basis of how we do everything.
Steve?
So, yep.
So the Hamiltonian that you write down looks pretty much like what I would write down if I were doing a dressed atom picture of, you know, a two-level atom in an electromagnetic field. Is there anything about it that would encourage me not to make that analogy perfect?
No, that's absolutely, it's a very close analogy. In certain situations, the fact that our atoms are actually weakly anharmonic oscillators rather than true two-level systems will modify the way you calculate this coefficient. But other than that detail, this is precisely derived by the dressed atom picture that you just mentioned.
Okay, super, thanks.
Yep, good question, thank you. What's interesting, one way to interpret this term is that the coefficient of A dagger A depends on the state of the qubit, and the coefficient of A dagger A is the cavity frequency. So in fact, when the qubit is in the ground or excited state, the cavity has two different resonance frequencies separated by 2 chi, which can turn out to be thousands of line widths. It's just enormous coupling. And therefore, if I wanted to make a quantum non-demolition measurement of the state of the qubit, I could just infer it by measuring the resonance frequency of the cavity, which I do by bouncing microwaves off of it. So, and this coupling Hamiltonian commutes with the thing that we're trying to measure, and therefore, to a good approximation, you can make quantum non-demolition measurements of the state of the qubit. You can read out the qubit. Now, this same term can be reinterpreted as saying, oh, the frequency of the qubit suffers a quantized light shift every time you add a photon to the cavity. Typically, chi is negative, so the spectrum of the qubit looks like this. It's a narrow line that sits here when there are no photons in the cavity, here when there's one photon, here when there's 2, 3, 4, 5, 6, and so forth. And this opens up the possibility that we can measure the state of the cavity, measure the photon number through its effect on the qubit transition frequency. So in particular, you could ask the question, is the photon number equal to 1? Yes or no? And you answer that by sending a microwave tone centered on this frequency, and you make it a pi pulse, which will flip the qubit if and only if there's exactly 1 photon in the cavity. So you do a conditional rotation unitary on the qubit through the angle pi, conditioned on there being exactly m photons in the cavity. I could choose m as 1 or 0 or 3, whatever I want. And again, this is unlike a photomultiplier. This is sensitive to different photon numbers, and it's non-destructive. You can repeat this measurement to increase the quantum efficiency and reduce the dark counts and so forth. So that's a very powerful way to measure, to ask the question. You're not asking the question, how many photons are in the cavity? You're asking, are there 7 photons or are there 3? Now, I'll show you an example later where there are 256 possible answers to the question. And so if you say, is the photon number equal to 1? Most of the time, the answer is no. So it's not very efficient, but I'll show you an exponentially more efficient way to do it later. Okay, so good. So, but in addition, you can ask other questions, smarter questions like, is the photon number odd? And you do that by simultaneously applying a tone, a pi pulse at this frequency, at this frequency, at the frequency corresponding to 5 photons and 7 photons. And so you can, in fact, make any measurement you want about the qubit spectrum. You can measure any binary valued function of the photon number. So for example, you could do a rotation on the qubit conditioned on any sum of the projectors onto different photon numbers where this coefficients are either 0 or 1. So you could make the coefficients 1 for all the odd numbers, for example. So this is extremely powerful. This is a way of measuring the parity of the photon number, which is extremely useful. It's also a way, as I'll show you later, of doing a binary, well, as I'm showing you now, I guess, a binary search. What is the photon number? And I do that by using as these little vectors of coefficients that go in here, the Walsh-Hadamard transformation of the photon number distribution. So that's just a fancy way of saying that, let's say it's like it's exactly doing a binary search. So you can ask in the first, you can do a conditional rotation on the qubit, which will flip the qubit if, so here's photon number 0, 7, 15. So if the photon number is in the upper half of the range of possibilities from 0 to 15, then flip the qubit. Then you can ask, okay, given that result, is it in the upper half of the upper half or the lower half, et cetera, and keep going down. And finally, is it even or odd? And if you think about that, that produces for you in 4 sequential measurements in a single shot. There's no, these are all QND commuting measurements. You get 4 measurement results, and you can turn those into the 4 bits in the binary representation of the photon number. So rather than saying out of 256 possibilities, let's say, you ask the question, is the photon number 3? That's not very efficient. Very little information is gained typically. But if you ask, you do a binary search, is the photon number in the upper half or the lower half of that range? You get in 1 bit of information with every query. And
Excuse
so,
me.
yep,
I have a question.
yes.
So in this measurements, there is a measurement of Z. And is this Z measurement done using this cavity, or there's a separate readout cavity for it?
Oh, good question. You could use the same cavity, but then you would destroy the
Yeah,
state.
that
Yeah.
was my concern. Like
So
if you use the
we
same
have
cavity.
we have another cavity, an ancilla cavity, which I failed to mention. I'll show you a picture of it later, which is used to interrogate the qubit. Thank you for pointing that out.
So this is Alicia. Can I ask another follow-up?
Absolutely.
So, in traditional binary, well, so you're flipping conditionally. Do you have to sort of conditionally unflip to do the next query? Because like if you
No.
had the photon number 15, then it would flip the first time and then flip back down the second time?
Right. So all you have to do is take these measurements, and from comparing this measurement and that measurement, you can tell whether this caused the bit to flip. And so that's this little algebra down here. The leading binary digit is this measurement result. And then the next measurement result is the sum modulo 2 of those two measurements. In other words, if,
okay.
Does that make sense? Yeah.
Yes.
Now in the actual experiment, what they really do is they reset the qubit to the ground state here, because this takes some time and you don't want, it lowers the odds of getting a decay event in the ancilla if you reset it first. So, but that's just a technical detail. So this is you can also do this determination by using the dispersive shift and phase estimation on this this rotation of the qubit. But that requires measurements followed by very rapid feed forward to make a slightly different unitary in each case. This binary search does not require any feed forward, so it's very efficient and simple. And furthermore, the circuit cost is only logarithmic in the range of photon numbers that you can sample. So there's an exponential gain over doing it the dumb way, asking first, is there 1 photon, is there 2 photons, are there 3, which in principle you could do in a QND way, but you'd have to go through n things on average to get the answer. Here you only have to go through log n measurements. So that's extremely efficient, and obviously much better than you can do in ordinary optics with photomultipliers, which are very hard to make number resolving.
Steve?
Yeah.
Now maybe I'm wrong about this, but it feels to me like the phase estimation way of doing things is closer to what, say, somebody like Hirosh does when he does QND measurements of the number of photons in a cavity. And well, first of all, is that right? Or
yes, it is right. And phase estimation also only takes log n steps. It's very, very similar.
Right. But what you're doing does have this advantage that you pointed out. And I'm wondering whether your ability to do that, does this have to do with the huge coupling that you've got? Because you've got a much better coupling than what
yes, the fact that the light shifted spectra of the qubit are highly spectrally resolved is the key here. That sets the speed limit at which you can do this.
Right. Okay.
Yep.
Thanks.
Yeah. Thank you. Good question. So this is a good place to ask if there are other questions.
I actually do have another question.
I'm shocked.
Yeah, I know. So I think I know the answer to this already, but when people say they make QND measurements, usually these things fall into two categories, ones that are truly QND and ones that are almost QND. And I guess what I really mean is every QND measurement is a little bit destructive, but the question is whether in principle there's a limit in which you can get the information you want, and in fact do no harm. And I'm guessing that your thing really does fall into that second category, that is a truly QND limit. Is that correct?
Right. It's not truly QND, but there is a limit of, if you could get the lifetime of the ancilla longer and, the dispersive coupling adjusted a certain limit to avoid the qubit causing the cavity to accidentally eat up photons from the cavity, then there is a parameter limit in which it becomes truly QND. At the present state, we can measure the parity about 500 times before we damage the parity of the state.
Okay.
So that's pretty close to QND.
Right. Yeah. No, absolutely. Okay. Yeah. I mean, the thing that I contrasted to is something like so-called non-destructive imaging, which is not non-destructive. It's just destructive.
Right.
Or minimally destructive.
No photons were harmed in the making of these,
Right.
the plots I will show you.
Right. Okay.
Okay.
Before
Good.
moving on, Charles,
Yes.
could I just ask one simple thing? Maybe it's not simple. Is there a way of measuring or asking questions about correlation functions? Like, is the photon field squeezed?
Oh, absolutely. Yeah, I'll show you some pictures.
Okay, thank you.
Yeah. Okay, so that was about an interesting kind of measurement we can do for state tomography. And knowing the photon number distribution, of course, doesn't give you full state tomography. But if you prepend that measurement with some displacements, then you have an overcomplete set of information to fully determine the tomography. We'll come back to that. So now let's talk about control. So we have our basic Hamiltonian, but we need to be able to make changes in the system, because in this Hamiltonian, the qubit state, sigma z, and the photon number are constants of the motion. But if I add a drive coupling to the electric and magnetic fields in the cavity, so I have a epsilon of t, I'm in a rotating frame here where all the carrier frequency that matches the cavity frequency has gone away. And I also put a drive, a Rabi drive on the qubit to change it from its value of sigma z. Then it turns out I can, through the presence of this nonlinear term, I can provably achieve universal control. And in particular, what this term can do for you is allow you to displace the cavity conditioned on the qubit state through the fact that the resonance frequency of the cavity depends on the qubit state. And it also allows you to do rotations of the qubit conditioned on the state of the cavity, because again, the qubit resonance frequency depends on the light shift. So from those two things, you can show that you can get universal control.
Steve,
yep.
So if this were optics, I wouldn't even bother asking this question, but since it's microwaves, it looks like you're making a rotating wave approximation.
Yes.
How good is that?
So let's see. So at the level of drives and detunings that we have, the answer depends on parameters and the situation, but it's extremely good in the context in which I will be describing it today.
Okay, just like in optics.
Yeah, exactly. Exactly. I mean, most of the stuff we know, we learned from you guys. So here's an example of a universal control. And here again is a peculiar kind of three-dimensional resonator. It's like a wave, it's like a quarter wavelength piece of coax, which is shorted at this end and open at this end. So it's a stub resonator in a circular waveguide. There's a little drive port that couples to the electric field that runs between the center pin and the outer wall. That's where our photons live. Here's the transmon qubit, and then here's that extra resonator that I mentioned when someone asked the question that we use when we use to read out the transmon. So this port can send in control signals to bounce microwaves off this resonator to learn the state of the qubit, or we can send tones at the frequency of the qubit in order to control it. It's all done by frequency multiplexing through these two wires. And we start the cavity in the vacuum state with no photons, and our target is to produce a unitary that maps us to this photon number 6 state. And by applying these predetermined, by solving the Schrodinger equation on a classical computer, and optimizing this pulse from some random starting pulse using grape, we can, with almost no subsequent tweaking, since we know the Hamiltonian so well, we can find a pulse which over time produces all kinds of crazy distributions. And then there's this magic interference at the last second, and all the quantum amplitude lands on Fock state 6. So here you see the distribution of photon numbers in the final state. And here you see the Wigner function of the final state. So the Wigner function is a kind of quasi probability distribution in phase space. Think of this axis as the coordinate of the harmonic oscillator, in this case, the electric field in the cavity. And this is the momentum, in this case, the magnetic field in the cavity. And you see the way that the key enabling technology to measure this thing, which is basically a Fourier transform of the density matrix, and therefore has complete tomography information in it. The key enabling resource is the ability to measure the photon number parity. If you want to know the Wigner function here, you displace the cavity with a drive to that point to the origin, and you measure the parity. So you see this beautiful circular symmetry. That's just the number phase uncertainty principle. The number is exactly 6, so the phase is uncertain by 2 pi. Here's an even more amazing state that you can produce with this control, and it's a squeezed state. It's a kind of Schrodinger cat made in Michel Deveray's group, living in 35 places at once in phase space. And the size of these little blobs are smaller than the 0-point uncertainty of the vacuum by, well, in energy by about 10 dB, because this is a squeezed state that Charles was asking about. And so this was first, these theorists invented these states proposing 20 years ago they'd be good for quantum error correction, but they were so ridiculously complicated that nobody thought they'd ever be made, at least I didn't. But last year, Jonathan Holm made them in the mechanical oscillations of the position of trapped ions, and made one state. Michel's group figured out how to stabilize a pair of orthogonal states, in other words, do quantum error correction. And using a certain sort of cooling and squeezing protocol, my postdoc Baptiste Royer has come up with a very clever improved protocol. And we discovered as we were writing it up that Jonathan Holm's group had the same exact idea, and they also have experiments coming out very shortly. So we're excited to see their results. Okay, so those are a couple of examples of measurement and control of these hybrid systems. And being able to measure the Wigner function is a very efficient way to do quantum state tomography. And it works much better than when you try to do this with multiple qubits with the same total Hilbert space dimension. It's just extremely simple to do. So now let's talk about hardware efficient simulation of physical models containing bosons. So, in general, two-level qubits, discrete variable systems, can efficiently represent spin-a-half quantum spin models because each qubit is mathematically represented by a spin-a-half. So that's fine. It's well known that fermions are hard because when fermions move in space-time and you interchange you permute their final positions, both of those Feynman paths can go to what is effectively the same indistinguishable final state, but they have a minus sign connecting them if there's an odd permutation between the two paths. And so that minus sign turns out to be very, very painful and makes fermion systems expensive and difficult to simulate on any quantum computer. But the bookkeeping that you have to keep track of these minus signs is quite complicated. It's less widely appreciated that actually bosons are also hard to simulate. So you might think, oh yeah, they must be somewhat harder because the boson number is unbounded. Although in practice, you can always set an upper cutoff. And as I showed you, it doesn't take very many, it takes only log of that cutoff number of qubits to have that same dimension of Hilbert space. So that's not so bad. And there's no minus sign, so that's not so bad. But it turns out that it's still difficult, and some of that is discussed here. And the reason is that physically natural operators for a boson Hamiltonian, for oscillators, such as the lowering operator B, which appears everywhere, are very unnatural and difficult to realize in qubits. So here is the qubit representation. If I had a cutoff of 7 photons, so I have 3 qubits and I have 8 states, 0 through 7 photons, then we know the matrix elements of B are just square root of n, and they lower n by 1. So sometimes you have to flip one of the bits, sometimes 2, sometimes 3. That seems like a complication, but actually you could use what's called the gray code. You could permute around the states that you use to represent the numbers of photons. And there would always be just one bit flip. But the problem is knowing which bit flips that's a function of all 3 bits. So it's or all n bits, however many you have. So it's a very complicated multi-qubit operation to represent something very simple. The oscillator lost a boson. So it turns out that bosons are harder to simulate on an ordinary qubit-based quantum computer than you might have thought. So that suggests that if you had an architecture with what we could call native bosonic modes, that is, it has both qubits and oscillators built in, then the oscillators could represent a very natural and highly hardware efficient way to represent the boson degrees of freedom. And that might be useful in lattice gauge theory, in studying phonons, in studying polarons, spin boson models. The Bose-Hubbard model has many interesting uses in atomic physics and condensed matter physics. And the example I'm going to talk about is simulation of the Frank-Condon factors in molecular vibrational spectra. And you might say, well, that's okay, that's sufficient for free bosons to have oscillators, but what if they're interacting or if it's anharmonic oscillators? But it turns out with this universal control it is possible to synthesize artificially arbitrary anharmonicities in the time evolution of our oscillators, but I won't go into the details of how that's done. There's a nice review here of sort of artificial materials, so to speak, made out of microwave light, and then talking about different kinds of simulations. Some of which are, some of the are not unrelated to the kind of thing that are done at JQI in Ian Spielman's lab and Mohammed Hafezi's lab. Okay, so we're going to talk about the molecular vibrations of the of some triatomic molecules. Molecular vibrations are approximately harmonic or maybe anharmonic oscillators, so their excitations are bosons. And we're going to try to very efficiently represent that Hilbert space with two microwave cavities. And you can have 3 microwave photons here and 5 there, and that might represent 3 quanta in one symmetry of vibrational mode and 5 quanta of vibration in a different symmetry mode. And so a typical optical spectroscopy experiment in a gas phase, let's say, in chemistry, you have, let's say, 2 vibrational modes. So there's a vibrational coordinate Q1 and Q2, and there's some kind of potential energy surface which is determined. This is the potential energy surface for the motion of the nuclei as the bonds stretch and shrink in the molecule. And the energy is the adiabatic energy associated with the bonds stretching and shrinking. It's the energy of the electrons, which are moving very rapidly and therefore can follow the nuclear motion adiabatically. And then once you have that potential energy surface, which is a 2-dimensional surface, you can quantize the energy levels of the vibrations in that surface. When a photon comes in and breaks, like promotes an electron to an antibonding orbital, it breaks a bond and produces a completely different potential energy surface. And it may have a different shape, it may be displaced, it may be rotated in the coordinate space. And if you make the sudden approximation that the photon suddenly moves you from one potential energy surface to the other by exciting an electron, then you calculate the Frank-Condon factors by looking at the overlap of the starting vibrational state in the 2D well with the various eigenstates of the new surface, the excited state surface. So you have to you have to find the square of the overlap of this initial state with each one of these possible vibrational final states. And then the energy change tells you the frequency of light at which this complex will absorb. So the photon energy goes into both exciting the electron to an antibonding orbital and changing the number of vibrations in the molecule. So I'm going to describe a first-generation experiment done by graduate student Chris Wang in the Shulkoff lab, published recently. We're going to, one use of quantum computers is to solve for the fermion problem to get these potential energy surfaces. We're going to use a classical computer and density functional theory and things like that. We're going to approximate the nuclear potential energy surface in these 2 coordinates as quadratic, so that these will be harmonic oscillators. That's an approximation. But we're going to allow for different curvatures in each direction and differences in the symmetry axes between, let's say, the ground state potential energy surface and the excited state potential energy surface. They can be rotated relative to each other, as well as displaced, squeezed differently, and so forth. And then in the sudden approximation, to figure out what's going on, you have to be able to execute the unitary transformation between the eigenstates of these two different Hamiltonians. And the chemists always cite this paper by Doctoroff, which explains an efficient way, moderately efficient way for doing that when you have a small number of modes. It's actually related to the computational complexity is related to boson sampling. It's in the same complexity class as boson sampling. So it's actually exponentially hard in the limit of an extremely large number of modes, even if they're harmonic. Okay, so so how do we do this? Well, what do we need to do it? And there's a list of requirements. You can see them in this nice paper in Nature Photonics, where people did this using optical QED. Of course, you need some bosonic modes, in our case, microwave photons, in their case, optical photons. And you need a bunch of Gaussian operations. You need beam splitters connecting the two modes, or however many modes you have. And the purpose of those is to produce superpositions of modes, or to produce a unitary transformation, which rotates the symmetry axis from the old surface to the new surface. You need squeezing, because there may be different spring constants in each of the modes, the two modes, and the two modes on the two surfaces. You need non-Gaussian state preparation, because you might want the initial state to have one vibrational quanta this way and three vibrational quanta that way, and you want to know the Frank-Condon factors for that particular case. You also need number resolved detection, because you're trying to find the spectrum. You want to know the probability of having all different numbers of vibrations in the final state. And I told you already how we do that number resolved detection. So these two things are challenging in conventional quantum optics. You can do squeezing, but it's hard work. But number resolved detection is very hard work for conventional quantum optics. Okay, so now here's the quantum circuit we use to do the Frank-Condon simulation. So we have a cavity A and cavity B. There's a coupler transmon qubit that connects them, and each cavity has an ancilla qubit connected to it, and not shown here are the readout cavities for the two ancillas. So the first thing to do is you use your universal control to initialize the system, so that each mode has a definite, like this has n photons, this has m photons, and the ancilla and the coupler and the other ancilla are all in their ground state. Then you carry out this Doctoroff unitary transformation that maps you from the states of one potential energy surface to the other. How do we do that? Well, that's shown in blow up over here. You first use the coupler transmon to squeeze cavity A, then you squeeze cavity B, then you turn on a beam splitter which rotates you between cavity A and cavity B through some angle that is determined by the rotation of the potential energy surfaces I showed you. Then you do some additional squeezing on each cavity. Then you apply a drive tone that displaces each cavity. So I haven't explained to you how you do squeezing, but again, with this universal control, it's relatively straightforward. Okay, and then you do a verification step. You check certain error flags to make sure they're zero. And those this unitary is supposed to carry out the Doctoroff transformation on the cavities, but leave the coupler transmon and the ancilla transmons back in their ground state. So you make sure that all three of those are in their ground state. If they aren't, something's gone wrong. There's been an error. This is not all possible errors, but it captures a lot of the errors. And so you post-select, you reject about 5 or 10% of the runs in which you find a flag error. One of the three transmons is not in its ground state. Then you apply the number resolving measurements in each cavity, and we allow up to 256 states from 0 to 15 in the first cavity photons, and 0 to 15 photons in the second cavity, using the method I described to you earlier. All right, so here is one example. It's photoionization of water, starting from the vibrational ground state of the stretch mode and the bending mode. And here is the theoretically calculated spectrum from our classical computer calculations. You can tell that we collaborated with chemists because of the units they made us use. And here is the experimental prediction from the simulations. When we measured we measured how how many photons were in each cavity by asking the question, are there 0, are there 1, are there 2, and repeating millions of times. So I'll call that the single bit readout. And the spectrum is Pij. So I means bosons in the first mode, and J means J bosons in the second mode. And this is the measured probability distribution, and this is the ideal. And this distance between the distributions is this sort of L1 norm of the difference is about 5%. So it's the fidelity in some sense is about 95%. If I do the boson sampling, which is exponentially faster, in this case 32 times faster, it requires more coherence in the ancillas because I keep them in running for a longer time. The accuracy is not quite as good. The infidelity is about 15%, but it's much, much faster. And if I just say, if everything were perfect in my measurements, but I had a little bit of self-Kerr induced in the cavities and a little bit of damping, photon loss, then solving the master equation suggests that the infidelity should be about 1.2%. So that's not bad agreement with that, and this is the best we could possibly do with the given decay rates we had. Here's a different thing with ozone ion losing an electron. And here we don't start in the ground state, we start in the vibrational state with 1 quanta and 2 quanta in the stretch and bending modes. And here the distance between ideal and measured is about 10% with the single bit measurement, 15% with the faster sampling. And the master equation says the best we could do is about 2.2%. But again, not bad. And you see a very different shape of spectrum, partly because it's a different molecule and partly because it's a different starting state. So again, I want to emphasize that we have this very efficient way of doing actual number sampling. So we measure a total of 16 states in each of 2 cavities, so 256 possible states overall. And we get them by measuring the first 4 binary digits in the photon number in each of the 2 cavities. And the circuit complexity is log of 256 rather than 256. Okay, and then finally, you know, using the microwave bosons to simulate vibrational bosons is highly advantageous. It's natural for the hardware. If we had tried to do this with 2-level qubits, we would have required at least 8 qubits, actually more, and at least 1,000 gates in what I'll call an ordinary quantum computer. So obviously, we're comparing our results to the exact calculations which were done on a classical computer. So we can't claim quantum supremacy over classical computers. But in a funny sense, this demonstrates strong supremacy over all other existing qubit-based quantum computers, because no one can do circuit depth of 1,000 these days. So future directions, we're thinking about the vision process. There's a conical intersection in the potential energy surfaces where the gap closes, and there the Born-Oppenheimer approximation that the electrons are the nuclei move adiabatically in an energy surface determined by the electrons breaks down. And this forms a kind of funnel where there's some dissipation. The photon comes in, puts you here, you rattle down, and then you either fall this way into cis-retinol or trans-retinol. And one of those two polymerizes a chain reaction that causes your optic nerve to fire, which is how you see. And this is getting harder to simulate on classical computers, not impossible, but it's a very interesting challenge. And so we've got an experiment that Chris Wang is working on to try in the early stages to try to do that. We want to try a different algorithm, quantum phase estimation, in order to add anharmonicity to the potential energy surfaces. And I'm also fantasizing about, you know, many-body boson problems like the fractional quantum Hall effect for microwave photons. So I'll stop there. One can fantasize about building large arrays of cavities for the purpose of simulating boson lattice models or doing quantum computation using bosonic qubits that have sort of built-in error correction, something that I didn't have time to talk about today. So here's the group. Here's Chris Wang, who did the experiments in Rob's group. And we talked extensively to actual chemists to educate us on spectra of molecules. So thank you very much. I'm happy to take questions.
Maybe I could ask a question. This is Steve Ralston.
Hi.
Hi, Steve. This is probably a stupid question, but I guess I don't understand why this is computationally a hard problem. I would have thought I calculate my Born-Oppenheimer potential for the ground state and the excited state.
Yeah.
Solve Schrodinger's equation and evaluate overlap integrals. So where is the computational complexity come in?
So imagine, so this is for harmonic surfaces, this is morally equivalent to having an optical table with a bunch of input fibers that feed a big network of beam splitters. And if you put coherent states in and you do homodyne detection at the output, that's a computationally trivial problem. You can work out how the classical waves travel through the beam splitters and get the amplitude of the waves at the output. But if you put in Fock states, like some number of photons in each of the input ports, and you ask what's the probability of getting some number of photons at each of the output ports, then you have to take the propagator, you know, the Green's function, the amplitude for a coherent state to go from port A to port B on the other side. You have to take that and you have to form all possible, there's a big matrix, the amplitudes to go from here to there. And you have to compute the permanent of that matrix, not the it's like the determinant, but with no minus signs. You would think that would make it easier, but actually the permanent is exponentially hard to compute exactly. It's not exponentially hard to approximate. It's a whole story there. So the Scott Aronson, proposed this boson sampling problem as a quantum supremacy task for quantum computers. And these Frank-Condon factors are exactly essentially in that class. And it's not hard to do for 5 modes, but if you had 100 modes, a classical computer is going to have serious trouble.
Can I ask a question? So Alexei Gorshkov.
Hi.
Hi, Steve. So here's the question. So it's about error correction. So I've always thought it was ridiculous, that people encode these, bosonic modes into qubits. I mean, it's insane, right? This John Preskill's, 5 to the 4th paper where they just go to so I've always thought it's crazy, and we have all of these nice bosons. So I'm totally with you. And then the thing that I was thinking about, maybe I asked this question, a couple of years ago. I discussed it also with Victor Albert, and I think even with John Preskill. So, but how about error correction? So what if you want to do this, a simulation of bosons with bosons, but also want to do error correction? So this would sort of require you to encode, a boson in, maybe in 1 or more bosonic modes in a way that would allow you to do error correction. And so I've thought about it and, discussed it with these people, and it actually seems, there's actually no sort of nice way of doing this in a way that would sort of make this mapping natural. I mean, you could make this mapping up to like some photon number, but it would be just end up being almost now as ugly as mapping it onto spins. So do you have anything to say about this
Yes,
error correction?
I do. So you can, there's 2 kinds of error correction. You can use continuous variables, bosonic modes, to encode a discrete variable, like a GKP state or these binomial codes we invented or the cat codes. You can represent qubits, and you can, but because the error model is very simple, there's only, 1 cavity and it has basically 1 error. It loses photons. And if you're, it's much simpler to do error correction. And that's why only bosonic codes so far have reached the break-even point for error correction. But that's representing discrete states. If you wanted to do boson sampling, where you want to maintain the bosonic character of the modes and do error correction on that, that's a much harder problem. But there, I'm a minor co-author on a paper by Liang Zhang and Kyung-Ju No, where we asked that question, and there is an answer using GKP states as non-Gaussian resources to correct, in principle, all of the states of the entire oscillator, only in principle. So I can direct you to that paper, which attempts to answer that very question.
Cool. I'll find it. Thanks.
Yeah.
Hi, this is Alicia again. Can I ask a follow-up to Steve Ralston's question?
Yeah.
Okay, so I think I must have an incorrect naive picture of a Frank-Condon. So if I have 2 displaced harmonic oscillators,
Yep.
then analytically, I know exactly what the 0 and the 1 and the 2 states are.
Absolutely.
And so it doesn't, it's a somewhat nasty numerical integral, and maybe if you're a theorist, it's even a possible analytic integral to just calculate the overlaps.
Right.
So what am I missing?
So it's not hard to do for small numbers of modes, but remember, we're also allowing the modes to rotate amongst each other between the ground and excited states. And it's there that it turns into the boson sampling problem. That's like having all these beam splitters on many different paths. So again, you can do it easily for small numbers of modes, but if you had, let's say, 100 modes and an arbitrary unitary rotation between the modes between the ground and excited state, then you have to compute these permanents. There are recursion relations that people use to calculate Frank-Condon factors become computationally exponentially hard when you have a huge number of modes which are mixed together. Yeah, so it's, yeah, I mean, everybody has that reaction, including me. I mean, it's how can this be hard? There's recursion formulas and stuff. And I've had chemists. I mean, I gave this similar talk at the University of Virginia, and there was a chemist who was actually an expert and had invented some of these recursion formulas. He said, it's not hard. And it took a couple days of email exchanges before he said, oh yeah, it is hard when you have a large number of modes.
Okay, so it's just you're getting this proliferation of massively oscillatory things, and the recursion
Yeah,
relation
exactly.
is
Yeah,
blowing up, and so it's just a
that's
mess.
right.
Okay.
That's right. It becomes classically intractable. To do exactly. It's a subtle complexity class. It's not so hard to do it approximately, it turns out. If you're interested in the big peak, you know, it has to do with whether you want to get the spectrum to a fixed percentage accuracy. Like each line should be good to, the height should be good to 99%, or you just have some additive noise. You lose some weak ones in the floor. It's a subtle complexity class.
Thank you.
Yep.
So Steve, this is Bill. So just to summarize what that discussion was, there's an exponentially large number of easy calculations that have to be done. Is that a fair way of saying it?
Yeah, that's one way to say it.
Okay. Now I've got an actual question. One of the things you said was that compared to doing this with optics, one of the big advantages you have is photon number resolving non-destructive detection.
Yep.
Now, more and more we're getting, because of these transition edge detectors in optics, we're getting photon number resolving detection,
Yep.
but it's still destructive. So how important is the one compared to the other? That is, the number resolving compared to the destructive.
So that's a good question. It depends on your dark count and quantum efficiency, and whether you need to take advantage of the Q and D-ness in order to beat those down.
Yeah.
So I made a suggestion a few years ago in a preprint with Konrad Lehnert that this ability to detect single microwave photons might be a way to dramatically speed up axion dark matter searches. Axions are putative particles that turn into microwave photons under certain conditions. And Aaron Cho has a nice preprint out. He's at Fermilab, where he has 4 orders of magnitude below the standard quantum limit for, you know, where you use ordinary amplifiers to detect these photons, and mostly you just detect vacuum noise. But if you can count the photons, and if you can not have dark counts, then you can do 4 orders of magnitude better. And the way that you get that is by repeating the measurements and taking advantage of their non-demolitionness.
Right. Gotcha. Thanks.
Yeah. There's a different dark matter experiment going on at Yale using the other half of the paper with Conrad's half, using 2-mode squeezing in a Yerke interferometer scheme to speed up the dark matter search. So there's a lot of places where quantum optics ideas are now entering, quantum sensing ideas, and now entering high energy physics.
This is Paul Julian. I have a question.
Hi, Paul. Long time no see.
Yeah, true, Steve. Long time since I've been at NIST. In the Frank-Condon system, it's well known that if you have these coupled oscillators, you can generate complex chaotic dynamics. And I presume you're experimentally in a regime where you're very far from that. But would you ever get in a regime where your system would go in some sense unstable or chaotic or experimentally? Or is that something either you would need to try to avoid, or could you actually get something positive and useful out of a complex dynamical system like that?
Yeah, so the present very simple and harmonic system that we have is that doesn't suffer from that
Right.
problem, but that's very, very interesting physics, of course. So it can occur that you can dump vibrational energy, as you know much better than me, into a particular mode, a particular pair of atoms oscillating or something, and then it can very quickly fan out across many, many modes in the system due to anharmonic couplings to those other modes. It can also occur that, because of anharmonicity, that mode has trouble matching the frequency of other modes, and it stays trapped. So in the former case, my understanding is that, you have many modes, and it kind of the energy irreversibly goes off into these other modes. And the classically, that would be a signature of chaos, for example, the quasi-irreversible behavior. So that's one of the things that we fantasize about being able to study when we build this larger simulator that's now under construction that has 9 modes in it. But it's still early days in our ability to control these larger and larger systems better and better. So it's physics we hope to explore, but we're not sure yet whether we're going to be able to make it work.
Okay. Yeah, thanks. No, I thought it might be possible at some point you might be able to do something with it, but yeah, not at this stage yet, no.
Right. The thing we've done is, pretty not actually interesting to chemists. I mean, they can do these calculations very easily, but these more complicated systems and thinking about quantum control of these more complex systems, is there a way to beat that chaos or take advantage of it by changing your control drives? That's the kind of thing you could explore on a simulator like this, but we're going to need a few more years of technical progress.